Is my screen visible?
Yes, sir.
Okay, great. So today we are going to do special functions. That's the third module. So we will begin special function with recollection of Legendre functions, which you have already done probably in your BSc. Vishal, Riba, I hope you remember, no? Legendre functions, Legendre polynomials. Vishal, are you there?
Yes, sir.
Yeah, yeah. I hope you remember. Jamu is here. He hasn't joined it. Okay, so these three will remember. We had discussed in their during their BSc during their third semester. We had discussed Legendre functions in great detail. So here we are going to go a step further, and we are going to talk about what are known as associated Legendre functions. That's what is required. But before I go to associated Legendre functions, I'm not sure if the rest of you how well versed you may be about Legendre functions. So we're going to just have a little bit of recollection, a recap of the Legendre functions, and then we will go to the associated Legendre functions. Okay. All right. So let's proceed. So this is what we're going to do. We're going to talk about first the Legendre equation, then the Legendre functions of the first kind, followed by the Legendre functions of the second kind. Then finally, this is when we do the Legendre functions of the first kind, we will encounter what are called as Legendre polynomials. Then we'll finally have a look at what are the properties of these Legendre polynomials. Then after that, we'll move on to the associated Legendre functions. So first, going to the Legendre equation. So what is the Legendre equation? It is basically a differential equation which is of this form. Okay. A Legendre function is a, I think I should make it a little bit bigger. Yeah. Is it visible now? Everyone? Are you able to see clearly? Okay. So, yeah.
Have you recorded the class?
Yes, it's recording. See this red color dot here on top?
Okay, sir.
This means it's recording. No, don't worry about it. It's just that Google is not allowing me to record. That's the thing. There's some issue with the university's Google account, so that's why. So anyway, so let's proceed. So what's a Legendre differential equation? Any differential equation which looks like this. Okay. So we have y double prime. What is y double prime? What does this mean? What is the meaning of when I write y double prime? What does it mean? Yes, correct. That's the second derivative. Okay, y double prime means second derivative. In physics, of course, there is a convention here. Can anyone tell me what's the difference between these two? Let me write this here. Now that we are talking about these primes, what is the difference between this? Just a minute. Okay. So we have y double prime. This means, all right, let's start with y prime. Y prime means the first derivative. So dy by dx, right? And y double prime, it means the second derivative, d square y by dx square. This we already know. In physics, we have one more notation, and that notation is we use a dot. What does this mean? And sometimes we use double dot. What's the difference between dot and prime? Putting a prime and putting a dot. What's the difference?
Sir, it is differentiation with respect to time.
Very good. So this is differentiation with respect to time. So dy by dt, and this is d square y by dt square. So remember, in physics, now over here, of course, we are discussing mathematics because it's mathematical physics. So in physics, this is a convention that we generally follow. Okay, the convention is this implies, a dot implies differentiation with respect to time. Okay, and a prime implies differentiation with respect to space. Okay, why did we come up with such notations, y dot and prime? Simply because, do you know the reason? Why have physicists come up with these notations? Anyone? Vishal, you know the reason, right? Vishal? Reba, you know the reason, right? I told you all during your BSc. What's the reason? Why did we have to come up with these shortcuts? Physics people, why did we come up with shortcuts?
Lazy.
Yeah?
Because we are lazy.
Yes, very good, very good. Never forget that, okay? Physics people, we are lazy people. So always try to come up with shortcut ways of representing something else. So that's why primes and dots, we use it very extensively in physics, okay? We are very fond of things which which take, lesser amount of time and space, okay? So that's what, economy of time and space, that's what we're interested in. Okay, so here this double prime, y double prime means the second derivative of y with respect to x. So if we have a differential equation of this form, the second derivative of y, it is multiplied with 1 minus x square. Then the first derivative of y, it is multiplied with minus 2x, and y itself, it is multiplied with L into L plus 1, where L is any real number. Okay, so if I have a differential equation of this form, then this is known as a Legendre differential equation. By the way, can anyone tell me, is this a homogeneous or an inhomogeneous differential equation? This differential equation, this Legendre differential equation that we have on the screen right now, this one, my question is, anybody who knows the answer, you can respond. This differential equation, is this differential equation homogeneous or inhomogeneous? Anyone? Is it a homogeneous or an inhomogeneous differential equation? Can anyone tell me? Do you know what is a homogeneous or inhomogeneous differential equation? Any idea? You have to know this, okay? Because next semester you're going to have the paper called as electrodynamics, okay? So in electrodynamics, the paper is all about solving the Maxwell's equations. So when you solve the Maxwell's equations, which are basically a bunch of differential equations, so two of the Maxwell's equations are homogeneous and two are inhomogeneous. So you have to know the distinction between homogeneous and inhomogeneous. So can anyone tell me what is this homogeneous or inhomogeneous? Just give it a shot.
Sir, inhomogeneous.
It is inhomogeneous. What is an inhomogeneous differential equation?
Sir, as far as I know, the powers of x are different here.
No,
Powers of
no,
y.
no. That's not what homogeneous or inhomogeneous means. So what it means is basically this. In this differential equation, we have two variables, right? So we have an independent variable, right? Okay. So which is the independent variable here? And then we have a dependent variable, right? So which is the dependent and which is the independent variable in this differential equation? Which is the dependent and which is the independent variable? Very simple. Just see what are you trying to differentiate with. Okay, so we have this y prime over y double prime. So what does y prime means? Y prime means dy by dx. So you're trying to differentiate something with something else. So always what you're trying to differentiate with, and with respect to what are you trying to differentiate it. This is a, what is on top, this is a dependent variable, and what you're trying to differentiate with respect to, this is usually the independent variable. Okay, so here which is the independent variable? The independent variable is x and the dependent variable is y. Is that clear, everyone? Just see what are you trying to differentiate with. Okay, so now that you know the dependent and the independent variable, just ask yourself, how many terms do I have? So there are three terms, right? There are three terms in the differential equation. Okay, we don't consider the zero to be a term. There are basically three terms in the this differential equation, okay, or any differential equation. So in a homogeneous differential equation, can you see the three terms? Which are the three terms here? This is one term, right? This is one term, this is another term, and this is another term. So these are the three terms. Okay, these are the three terms of this differential equation. Okay, So in a homogeneous equation, what happens is every term contains either the dependent variable, every term contains the dependent variable and or its derivatives. Okay, if this is true, if look at every term, if it contains the dependent variable and or its derivatives, then it's a homogeneous differential equation. Now tell me, is it homogeneous or inhomogeneous?
Sir, inhomogeneous.
How is that so? Which is the dependent variable? The dependent variable is y, no? Yes or no? The dependent variable is y. Look at the first term. Does it contain y or its derivatives?
Yes, sir.
Okay, I should make it clear. It contains the dependent variable and or its okay, not only. Okay. So the first one, does it contain y or its derivatives? Yes, it does. Second term, it does, right? Third term,
Sir, only dependent variable.
yeah. No, not only. It can contain the independent variable, but it has to contain the dependent variable and or its derivatives. Just ask yourself this question: does the first term, does it contain? Okay, it contains. Okay, does it contain the dependent variable and or its derivatives? Yes, it contains y double prime. Second term, does it contain the dependent variable and or its derivatives? Yes, it contains. The third term, yes, this also contains. So all the three terms, they contain the dependent variable and or its derivatives. So it's a homogeneous differential equation. But if suppose this same differential equation, if it would happen in this form, okay, suppose I write the differential equation like this. So 1 minus x square y double prime minus twice x y prime plus L into L plus 1 y minus e to the power minus x square is equal to 0. Now consider this differential equation. Here how many terms are there? Let's look at the terms. This is the first term, right? This is the second term, this is the third term, and there is one more term, this is the fourth term, right? So first term, term number 1, term number 2, term number 3, and term number 4. So now ask yourself this question: does it contain the dependent variable and or its derivatives? Yes, it does. This also does. This also does. What about this one? Does it contain the dependent or its derivatives? No, it does not contain. So this differential equation, this is an example of an inhomogeneous differential equation. Is this clear, everyone? Okay, so now you know how to distinguish between homogeneous and inhomogeneous differential equation. So the Legendre differential equation, it is a homogeneous differential equation, right? So now this has got regular singular points. The Legendre differential equation has got something called as regular singular point. Okay, so now what exactly is a regular singular point? Does anybody remember? What is a regular singular point? Anyone? What is a regular singular point? Anyone? Do you know? Yes? No?
No, sir.
Okay. Okay, somebody is searching Wikipedia. That's all right. Okay. Now let me try to show you over here. Okay. So we define a point, let's say x naught is a regular singular point. Okay, a point x naught is a regular singular point of a differential equation. Okay, of, let's say, of the differential equation. Which differential equation? The differential equation, let's say it looks like this. There is some function p of x times the second derivative of the dependent variable plus some other function q of x times the first derivative, then another function r of x. So p, q, r, these are three functions of the independent variable alone. Okay, why this is equal to 0. So suppose I have a differential equation of this form. So a point x naught is a regular singular point, okay, of the differential equation if the following two conditions they hold good. Number one, the first condition is if suppose I take the ratio of q by p. If I take the ratio of q of x divided by p of x, and this ratio I multiply with x minus x naught. Okay, so suppose I take this ratio and I multiply with x minus x naught, and whatever I get, let us say I take the limit of this as x tends to x naught. Okay, and similarly, okay, rather I should say if both this limit and this limit the other limit is, instead of q in the numerator I take r, and I this one instead of x minus x naught, if I take x minus x naught whole square. Okay, if both of these limits are finite, okay, if both of these are finite, then this point this is a regular singular point. Okay, so now let's just apply this to the case of a Legendre differential equation. So let's take this case of a Legendre differential equation, which is let me write this down. It is 1 minus x squared to the power 1 minus x squared into y double prime minus twice x y prime plus L into L plus 1 into y is equal to 0. This is the Legendre differential equation. Now compare it with this one. So let's call this as equation number 1 and let's call this as equation number 2. So comparing equations 1 and 2, so comparing equations 1 and 2, what do we get? We realize that p of x is nothing but 1 minus x square. What is q of x and what is r of x? What is q of x and what is r of x? Compare 1 and 2. Tell me what is q of x. What is q of x? Minus twice x. Minus twice x. The minus sign also has to be included. And what is r of x? It's a constant function, L into L plus 1. Okay, this is r of x. Now what we need to do is we need to evaluate these limits. Okay, so let's take the limits. First limit is q by p into x minus x naught. So let us say at x equals, let's say x naught equals, let's say plus 1. Okay, when x naught is equal to plus 1, let's try this out. So we have of course from here, let me just take the ratio also. So q q of x by p of x is equal to minus twice x divided by 1 minus x square, and r of x by p of x is equal to L into L plus 1 divided by 1 minus x square. This is what we have. So now let's say x not equal to 1. So I want to find out this limit. So limit as x tends to x naught, which is 1, of x minus x naught, which is x minus 1, times this one, q of x by p of x. Let me just grab this from here. What will this be? What's this going to be? So this is equal to, the denominator I can write it as 1 minus x square. I can write it as 1 plus x times 1 minus x. So we have 1 minus x and 1 plus x. What will happen is this will cancel out this with a minus sign, because this is x minus 1, this is 1 minus x, so it will give us an additional minus sign. This minus and this minus will cancel out, and eventually what we're going to have is limit as x tends to 1. So we're going to have, in the numerator we're going to have 2x, in the denominator we have 1 plus x. We can now simply replace x with 1 because it's not going to make it infinity or so. So this is going to give us 2 divided by 1 plus 1, which is equal to 1, which is finite. Okay. Likewise, we also have to evaluate this one. Okay. We have to evaluate this quantity. Okay. So I'll leave it to you. Okay. The homework for you to verify. So evaluate, or rather I want you to verify the same for x naught equals minus 1. You will find that for both x equal to x equal to plus 1 and minus 1, for both of these you will find that these limits, both of these limits, they turn out to be finite, and that means x not equal to plus or minus 1, that is these are two regular singular points, okay, for the Legendre differential equation. Okay, so here we have L is a real number. Okay, any solution of this equation number 1 is known as a Legendre function. Why do we need to study Legendre function? Because it occurs in many physical problems which have got an axial symmetry. Okay, so when in those problems where we have some kind of an axial symmetry, their Legendre differential equations they become very popular. Okay, we'll do some problems next semester in your electrodynamics course. You will see, we'll take some cases where there is some charge distribution which has got some axial symmetry, and we will see that the Legendre differential equations, actually they come into the picture. In fact, I think I have an example right here itself. So in such cases what happens is x is simply replaced with cos theta, which is allowed. Okay, we can replace x with cos theta. Why is that so? Because you see there are regular singular points, right? What are the regular singular points? The regular singular points are x equal to plus or minus 1. That means this one will have a solution, and as we will see, it will have a finite solution and it will have an infinite solution. There will be two linearly independent solutions. So one will be finite, one will be infinite. The infinite solution, that will be converging only between plus or minus 1, and a finite solution, of course, it's just going to be a polynomial, so we don't have to worry about the convergence. Okay, but the infinite series solution, that will have a convergence, a region of convergence between minus 1 and plus 1. And cos theta, we know, is a trigonometric function. The range of values of cos theta, it lies between minus and plus 1. So we can replace x with cos theta, and write this in the most general solution. We can replace x with cos theta, and that is going to give us and that is going to help us to apply the Legendre equation in case of spherical symmetry also. Okay, so now let's look at the power series solution of the Legendre equation. So what we do is we assume a solution. This is basically a power series solution. This was one of the first things that you do in your mathematical physics 2 course in your BSc. So we assume a solution of this form. We assume that y is equal to a n x to the power n, where n goes from 0 to infinity. Then we can just differentiate this, and this gives us y prime. So y prime will be n comes in front, so we have n a n, and x to the power, the power reduces by 1, so n minus 1. So this is the derivative of y, and then you differentiate once again, so y double prime will become equal to this n minus 1 also come up front, so we have n into n minus 1 a n x to the power n minus 2, because here the power is going to reduce further by 2 because of the second derivative. Okay, so now what we do is we just need to replace this y prime and y double prime. We just substitute it back in this equation number 1, and that is going to help us obtain what is called as the recurrence relation. So in equation number 1, what we do is we substitute y prime and y double prime, and then this equation number 1 takes this form, okay, where we have a summation, and then we use something called as shifting of indices, and we collect these terms. So shifting of indices is basically a method by which you can convert all the terms to ensure that all the terms have the same powers of x. Okay, the general in the most general term that x has a power of n. So then we can just take x to the power n common, and that whatever is left behind, okay, these are the coefficients of x to the power n. Okay, so now the moment we get something like this, then we know that the coefficients must be identically 0, because the right hand side is 0. So because x is arbitrary, the only way you can satisfy equation number 2 is if you ensure that the coefficients are also 0, because it could be possible that this if the coefficient is suppose non-zero, but let's say x is 0, that's a trivial case. Or maybe for some specific value of x, it may happen that this is going to be 0, but that will not happen for all values of x, okay, for the simple reason that x is arbitrary. So in order to satisfy equation number 2 at all times, the coefficients, the ones that we have over here, that coefficients must be identically 0. And the moment we make this coefficient 0, so you can see here n plus 2, n minus 1, a n plus 2 minus this one, here we have a n. You make this entire thing to be equal to 0, this entire thing, okay, make it equal to 0, and the moment you do that and then rearrange this, you find that you are able to write a n plus 2 terms in terms of a n. Okay, a n plus 2 you are able to write in terms of a n. This is basically the recurrence relation. We have already seen the recurrence relation yesterday when we are talking about the Poisson, the binomial distribution and the Poisson distribution. Recurrence relation is any relation which is such that if you know one term, then you can find out the other terms. Okay, if you, in this case, if you know one coefficient, you can find out the other coefficient. So for instance, if I know what is a0, right, then from a0, using this recurrence relation, I can find out a2, not a1. Okay, then from a2, using this recurrence relation, because here you see if n is 0, then this is going to give us n0, it is going to give us a2. So from a0 I am getting a2. From, if n is 2, from 2 we have 2 plus 2, we will get a4. From a4 you will get a6, and so on. So you can do these jumps. Likewise, let's say if I have a1, if I know what is a1, knowing a1 I can find out a3, knowing a3 I can find out a5, knowing a5 I can find out a7, and so on. So it means these two are your starting coefficients. Okay, there is, you have to know what is a0 and a1. Without knowing a0 and a1 you cannot proceed. Okay, so this a0 and a1, the choice of that, okay, that is what is going to give us the set of Legendre polynomials that we are interested in. So this is basically your recurrence relation. So the moment you get this recurrence relation, then we are now able to obtain linearly independent solutions. So like I said, you need to know a0 and a1 at least. Okay, so but a0 and a1, they are arbitrary, so it's up to you how you want to choose a0 and a1. So let us say for simplicity I choose a0 to be 1 and a1 to be 0. So if I choose a0 to be 1 and a1 to be 0, what does that mean? This scenario, what does it mean? If I choose a0 to be equal to 1, okay, this means from here we get a2 from the recurrence. From here we will get, or rather let me write it this way. So we have these different terms. Look at, remember the solution. What was the solution? The solution was, we had summation. We assumed that this was the solution. The solution was a n x to the power n, right? And when we expand this, n is 0 all the way till infinity. So when we expand this, we have a0 plus a1 x plus a2 x square plus a3 x cube plus a4 x to the power 4, a5 x to the power 5, and so on. Okay, so here we have chosen a0 to be 1. a0 is 1, that means this is non-zero, right? From a0 we will be able to find out a2, so this will also be non-zero. From a2 we can find out a4, so this is also going to be non-zero, and so on. Okay, but we have also chosen a1 to be 0. The moment we choose a1 to be 0, that means this is equal to 0. Okay, so this vanishes. Because this vanishes, because of the recurrence relation, this is also going to vanish. Because this vanishes, then the recurrence relation, this is also going to vanish. So as a result, when we make this choice, a0 is 1 and a1 is 0, we will have only even powers. You can see here x square, x to the power 4, x to the power 6, and so on. So this is what we're going to have. We're going to have even powers. The series is going to contain only even powers. Is that clear, everyone? Is this clear to everyone? Okay. Now if you choose the other way around, if I choose a0 to be 0 and a1 to be 1, then what happens? We have x1, because you know a1 into x1, a1 is 1, and then we will have the odd powers. Okay, 1, 3, 5, and so on. The even powers is they are going to become 0. So this is what we're going to have. Okay. All right. So we call this, the first one that we got, we call it as y1, and the second one we call it as y2. And this y1 and y2, you can see they are linearly independent. Okay. So these two are linearly independent. Can you see that? Can you see the linear independence of y1 and y2? What do I mean by linear independence? When I say two functions are linearly independent, what does it mean? Anyone?
So one can't be written in terms of the other.
Exactly. I mean, one cannot be written as some constant times the other. Okay. In terms of the other, we can write, but we cannot write one in one function as some constant times the other function. So you can see y1, it has got only even powers, y2 has got only odd powers. No matter what you multiply, whatever constant you want to multiply with y1, there is no way you can get y2. Likewise for y2, you can multiply as many constants as you want, but you can never get y1. So they are linearly independent. So we have a couple of linearly independent solutions, and these linearly independent solutions, okay, both of them they converge, both y1 and y2, they are convergent for modulus x less than 1. Where does this modulus x less than 1 come from? Where does this come from? Modulus x less than 1, it comes from this fact, this has got regular singular points at this plus or minus 1, this forms the boundary. This is where it comes from. Okay, I'll not go into the details of that, but just I want to give you help you recollect whatever you had done in your VLC. So because y1 and y2, both of them, they are convergent, so there is a radius of convergence of 1. By the way, y1 and y2, both of them are infinite series. Okay, so they will have certain radius of convergence, and you can find out the radius of convergence by using, how do you find radius of convergence? How do you find radius of convergence? We can use what is called as a ratio test, right? Remember, there are lots of tests for convergence. There's something called as a ratio test, which we had talked about in your complex analysis part also. Then we have what is called as a root test, right? So many tests are available. So using these different tests, we can find out what is the radius of convergence. Okay. And also y1 and y2 are linearly independent. So because y1 and y2 are linearly independent, so we can get the most general solution of equation number 1 as this: c1 some constant times y1 plus some other constant times y2. Okay. Now coming to the integer values, okay, let's take a special case. What is a special case? The special case is, if you look at the Legendre equation, it contains, there are three terms. The last term, the term which was with y, it contained L, and we say that L is a real number. If L is a real number, then it can take any integer and non-integer values. But we are interested in a special case where L takes only integer values. So let's look at what happens where L takes integer values. That gives us some really interesting results. So in many applications, L is an integer. The value of L, it goes from 0, 1, 2, 3, 4 and so on. Then using the recurrence relation, okay, because we have the recurrence relation. Let me write down the recurrence relation here. You will see something interesting happening. Okay, let me do it in the on the whiteboard. Let me grab the recurrence relation. Okay, so this is the recurrence relation. Okay, so if we have, let's say, if L is integer, okay, if L is integer, that is the value of L, it could be 0, 1, 2, 3 and so on. Then what we'll have is, we have these different coefficients, right? So we have A0, A1, A2, A3, A4 and so on, okay. And then we have, let's say, an minus 1, we have an, we have an plus 1, we have an plus 2, an plus 3, an plus 4. Let me just write a few of those. And so on, okay. This is what we have. We already know that if you know A0, we can find out A1, A2. If you know A2, you can find out A4 and so on. Likewise, if you know A1, you can find out A3, and if you know A3, you can proceed this way. Okay. In a similar way, if you know an, you can find out an plus 2. If you know an plus 2, you can find out an plus 4. If you know this, you can find the rest. Knowing an minus 1, you can find out n plus 1. N plus 1, if you know, you can find out an plus 3. Right? Is this clear? It sounds okay, no? This idea? Okay. Because you can just go, you can find alternate, the idea is you can find alternate coefficients. Using the recurrence relation, you can find out alternate coefficients. Now let us say L is an integer value. If L is integer, so for instance, let's say L is equal to, let's say 30, 30. Okay, then what will happen? Then n takes all possible values, 0, 1, 2, 3, 4 and so on. So n will definitely take that same value, that is L, right? So let us say L is an integer. So what will happen when n takes the value n is equal to L? Then what will happen? When n is equal to L, then what will happen? Then according to the recurrence relation, we will have A, just replace wherever there is n, replace with L. So we have L plus 2. This is equal to, and here replace n with L, L into L plus 1 minus, here already we have L into L plus 1, and in the denominator we have L plus 1 because n is equal to L, and L plus 2 times AL. Okay, what will this become? What will this become? This will become 0, right? Because these two cancel out, right? So AL plus 2 is equal to 0. So when n is equal to L, okay, so let us say this here, n is equal to L, okay, so this is non-zero, this is non-zero, but we see from here, this is n is equal to L plus 1, okay, here it is L plus 2 and so on. This is L plus 2, this is L plus 3, this is L plus 4 and so on. And we see from the, from this recurrence relation, what has happened here is, the moment n is equal to L, L plus 2, AL plus 2, this will be AL plus 2, this will become 0. If this becomes 0, then this will also become 0. Then the rest, everything else. So all of these next terms will become zeros. Is this clear? Is this clear, everyone? Okay, so what is the consequence of this? The consequence is basically this. Let me take an example. So we have y1. Y1 is, we saw here, y1 is it takes it has even values of x, even powers of x. Okay, so y1 is going to be, let's say, we have a0, then we have plus a2, or rather let me do it this way, graphically I'd like to show you. So the solution, original solution, we had a0, a1 x, a2 x square, a3 x cube, a4 x to the power 4, a5 x to the power 5, a6 x to the power 6, a7 x to the power 7. Okay, so this is going to be your y1. So y1 is going to be this plus this plus this plus this and so on. And what is y2? Y2 is going to be this part, right? This is what we have already established. Now let us say L is equal to 4. I'll just take an example. Okay, for example, let us say L is equal to 4. Okay, L is equal to 4 means here the value of n. Okay, for this case, n takes the value. Okay, the value of n takes the value 0, 1, 2, 3, 4, 5, 6, 7 and so on. Now we saw when n is equal to L. So when does n become equal to L? Over here. Okay, this is the place where n becomes equal to L. So here n is equal to L, which is equal to 4. And we saw from here, from this recurrence relation, when n is equal to L, L plus 2 will become 0. So if n is equal to L is equal to 4, that means we are talking about A4, right? So A4 will be non-zero. Okay, L is equal to 4. This implies A4 will be non-zero. And we have seen here, if A4 is non-zero, L is 4, then the next one, according to a recurrence relation, will be A6. What does this tell us? What does this tell us? It tells us that A6 will be 0. So which means this is going to be 0. Next, this is going to be 0. Next, this is going to be 0 and so on. So as a result, what happens is, earlier y1 and y2, they were all they were all infinite series, right? You can see here y1 and y2, they were both infinite series. But when L takes integer values and the moment n is equal to L, what has happened in this case? Immediately y1 is no longer an infinite series. Okay, y2 is still an infinite series. Okay, oops. Y2 is still an infinite series. So we can see here, so therefore y1 is no longer an infinite series. Okay, y2 is no longer an infinite series. What is y1 is no longer an infinite series. What does y1 become if it's no longer an infinite series? Do you agree? It becomes a polynomial. What is a polynomial? Definition of a polynomial: an expression which contains powers of x, right? And whichever is the highest power of x, that becomes the degree of the polynomial. Okay, so it has to contain finite number of terms, and these terms are powers of x. And because earlier y1 was an infinite series, so it was not a polynomial. But the moment L takes integer values, then y1 becomes no longer an infinite series, it becomes a polynomial. Okay, is this understood? Is this clear? Okay, but what about y2? What about y2? Y2 still remains. Y2 still remains an infinite series. It does not become a polynomial. Okay, and you can try it out for yourself. I'll leave it as a homework for you. Okay, so here what is the value of L? That is, L is equal to 4. That means L is even here, right? L is even here. I'll leave it to you as a homework. So you have to just verify. Okay, you need to check that when L is odd, then what happens is y1, it is y2 which becomes a polynomial. Okay, and y1, it still remains an infinite series. Okay, I'll leave it to you, just try it out. Instead of L equal to 4, let's say you take L equal to 5. Okay, you can verify for yourself. You will find that y2 now becomes a polynomial and y1 remains an infinite series. Okay, so this is what happens. This is the special case that we are interested in. So we have, when we consider this L to take integer values, then depending on whether L is even or odd, okay, so the series is going to terminate. Okay, either of y1 or y2, either of these two will terminate, either y1 or y2, and it is going to terminate, and it is going to give us a polynomial of degree L. So here both of them, when as long as L can be real valued, y1 and y2 both of them are infinite series. But the moment L is equal to an even integer, then y1 becomes a polynomial, y2 remains an infinite series, and the moment L takes a odd integer value, then y2 becomes a polynomial, it gets chopped off, y2 becomes a polynomial, and y1 remains a infinite series. So any one of these will become a polynomial depending on the kind of value that L takes, whether L is even or odd. Is this clear, everyone? Is this understood? Okay, so just try this out. Okay, once you try this out and once you understand this is going to become clear. Okay, so this takes us to Legendre functions. So what is Legendre functions? Like I said here, if L is even, then y1 reduces to a polynomial. If L is even, then y1 reduces to a polynomial of degree L, but y2 still remains an infinite series. Okay, then in that case y1 we call it as PLX and y2 we call it as QLX. So here notice the terminology, we use PL, okay, PL to denote a polynomial. Okay, and we use QL to denote an infinite series. Okay, both polynomial and infinite power series. Okay, not infinite series, a power series. I should be more specific here. It's a power series. Let me make the correction here also. Not an infinite series, it's a remains a power series, and in case of L is odd, remains y1 remains a power series. Okay, so there's a difference between a polynomial and a power series. Both of these contain powers of x, but polynomial is finite where power series is infinite. Okay, so we use this term. Yeah.
So for y2, then can we call it a function like power series of a function like sine function and all?
If you plot it, it will will it look like a sine function? Let's see. If you plot this, in fact the plot is there.
In general, like can we call it a
No, you can't call it a sine function, because sine function, the coefficients are different. Okay, it depends on the shape of the function, it depends
no,
on.
sir,
Then?
like not sine function, but in general, can we call it function
Yeah, you can call it a function.
if that is a polynomial?
Yes, it's a function. Polynomial is a function. Then power series is also a function, or rather, I should say, a function could have a power series expansion. That's the better, more appropriate way to put it. Okay, instead of saying that a power series is a function, polynomial is definitely a function. Instead of saying that a power series is a function, a more appropriate way of putting it is a function could have a power series expansion. In fact, that's what we will see. The QL, I'll show you some of the functional forms of this QL. Okay, I'll show you, don't worry. Okay, does that answer your question?
Yes, sir.
Okay, so this is what you need to keep in mind. If L is even, okay, remember we started with two we started with two power series, y1 and y2. These are two power series, as long as L is real. In general, L can take, you know, non-integer values, both y1 and y2, both of them will be power series. But the magic happens whenever L takes integer values. Then we find if L is even, then if L is even or odd, then one of these power series, it gets chopped down and it becomes a polynomial. So in case L is even, y1 becomes a polynomial, y2 remains a power series. In cases L is odd, y1 remains a power series and y2 becomes a polynomial. Either of these two cases, we reserve this term. PL is used for polynomial and QL is used for a power series. So we give some special names to this. PAL of x, that is a polynomial form. Okay, the polynomial function that we obtain depending on whether L is even or odd. This is known as Legendre functions of the first kind. And the power series form which we have, that is QL of x, that is known as a Legendre function of the second kind. Okay, so therefore the general solution of the Legendre equation, okay, for integral values of L will be a linear combination of PL and QL. Is that clear, everyone? So we are looking for a linear combination of PL and QL as a general solution of the Legendre equation. But remember, this is only for integral values, because for non-integral values, this is still the general solution. Okay, this is for integral and non-integral solutions. For integral or non-integral values of L, this is the most general solution. Okay, so I think I should make a clarification here. Therefore, the most general solution of equation number 1 is this. But whereas if you take integral values, then depending on whether it is even or odd, we will get two kinds of solutions. One is a polynomial which we call as PL, another one is a power series which we call as QL. So the polynomial, that function, we call it as the Legendre function of the first kind, and the power series we call it as Legendre function of the second kind. So the general solution will be a linear combination of these two. Now let's have a look at Legendre functions of the first kind. So we already saw it depends on it is obtained from either y1 or y2. Okay, so we cannot say that the Legendre function depends only on y1 or y2. It depends on both y1 and y2 depending on whether L is even or odd. So if L is even, it will be y1 times some constant. Okay, so these are basically, this is a normalization constant mu L. If it is an L takes an odd value, then it will be y2. We have already seen that, right? If it is even values, then it is the y1 which gets chopped off. If it is odd values of L, then it is y2 which gets chopped off. So for even values, PL depends on y1. For odd values, PL depends on y2. And there is some, we need to normalize this because generally it is expressed in normalized form. So to normalize this, we need certain constants, and this mu L and nu L, these are your normalization constants. So now let's look at PL as a finite series, the form of the finite series. So this is the form. This, by the way, the derivation is there in your BSc course. So I'll not go into the derivation of this one. If you're interested, you can have a look at the book by Benz, okay, which I have already shared in Moodle. You can go through. And there is a chapter on special functions. So over there, the derivation of this formula is there, this series formula. If you're interested, you can see. And as you can see here, it's not an infinite series, it's a finite series because there happens to be an upper limit of the summation. And this upper limit is m, and this m depends on, if it is even L, it is L by 2, and if it is odd L, then that is L minus 1 by 2. Then these are called as your Legendre, the famous Legendre polynomials. Okay. So how do we normalize this? Because remember, we have this normalization constants here. So how do you normalize this? So there is a convention that is usually followed for normalization. The normalization is PL is normalized in such a way that the value of all the Legendre polynomials at x equals 1 will be 1. All of them, they will pass through x equals 1. They'll pass through the same point. Okay. So what does this mean? It means all the Legendre polynomials, you will see that from the graph. Okay, so all the, or rather let me put it on the slide. So this is the convention for normalization. Let me put it here. Once I show you the plot, then it will become clear. Okay, so what does this mean? This one, what does this mean? This implies all the Legendre polynomials, okay, that is for every value of of L, they pass through the point x equals 1, y is equal to 1. 1 comma 1 means x equals 1, y equal to 1, because all of them should have the same value 1 at x equals 1. And what about x equals minus 1? X equals minus 1, it depends on L. Okay, so if we are talking about L equal to 1, so we'll have something like this. So we have a minus 1 here, this is minus 1, this is minus 1, this is plus 1. So what will happen is all the points, this is also plus 1, plus 1 1, this is the point, right? 1 comma 1, this is the point. So you'll find that all the Legendre polynomials, they'll pass through this point. Okay, but what about when x is equal to, this is x, okay, and this is PL of x. But what happens at minus 1, x equals minus 1, then what happens is the value of the Legendre polynomial will depend on whether L is even or odd. So if L is even, then this is going to become 1, because minus 1 to the power even value, that's going to give us plus 1. So that is going to pass through this. Okay, so it's going to pass through this for even values of L. And for odd values of L, this is going to give us minus. So they will pass through these points for L odd values. Okay, so this is what we expect from the way it is normalized. So the first few Legendre polynomials, the functional form of the first few Legendre polynomials, these are the first few Legendre polynomials. So we have P0 is 1, P1 is x, P2 is half 3x square minus 1, and so on and so forth. So just first 5 I have just given the functional forms. You have higher order Legendre polynomials which you can work it out using the there is a formula which actually helps you to work out the Legendre polynomial. There is a recurrence relation also which helps you to find that. Okay, so this first 5, not 5, these are the first 6, because it starts from 0, right? So these first 6 Legendre polynomials, I have also plotted them here. So let me show you the plot. Yeah, so this is the plot of the first few Legendre polynomials. Okay, let me take this to the slide. Then you will see that normalization convention that I have mentioned, you will see that is being satisfied. Okay, let me grab this. Okay, so this is what we expected. Okay, this is what we expected. Let's see if it is really following this. You can see, for one thing, the first one, all the PL of x, the first normalization convention, it says that all of them, they should pass through the same point, and we see that exactly the same thing has happened. Can you see that? They are all passing through the same point, correct? This point, this is your x equals 1, and this is your y equals 1. So this point is your 1 comma 1. Is that clear, everyone? Is this clear? Okay, then what about this one? If L is even, then they'll pass through this point. Okay, this point is your, here this is minus 1, this is plus 1, and on this side we have minus 1 for the y-axis. So this point is minus 1 comma plus 1, and this point is minus 1 comma minus 1. We said that if it is even, it will pass through this point. You can see it for yourself. Here the blue plot is P0. This is the blue plot, P0. P0 passes through this point, right? Then next even one is the green line. The green, it is P2. Which is P2? P2 is this one, the green curve. You can see this also passes through this point. Then which is the next even one? P4. P4 is this what is this color? Violet color. Okay, this purple color. So this passes, where does it pass through? Again, you see that it passed through this one. So all even values, wherever L is even, it is passing through this point, and wherever L is odd, it's passing through this point. You can see P1 is that orange line, passes through this. P3 is this red color line, this is the red color line, passes through this. P5 is this brown colored line, this is this brown colored line, which also passes through his. Okay, So these points where these these different polynomials where they converge, this point, it depends on exactly why are they converging at this point. It is because of this convention of normalization. Because of that we are having this behavior. Okay, is this clear, everyone? Any questions? Okay, so now let's proceed. So these are the first 5 polynomials. Now let's look at the Legendre functions of the second kind. Okay, so depending on whether L is even or odd, the Legendre functions of the second kind, they are defined in this way. As we already saw, if we have even values of L, then y1 becomes a polynomial, then y2 remains a power series. That means QL will be y2. Okay. Similarly, if it is odd values of L, then y2 will become a polynomial and y1 will remain a power series. And so QL will be proportional to y2 for even L, and it will be proportional to y1 for odd L. And we have two constants, alpha 1, beta 1. These are your normalization constants, just like before. And as per convention, this is how we take these normalization constants. Okay, so this Q1 and Q2, this is a finite infinite series which converge, or rather I should say it's a power series. QR power series, more appropriate word will be power series. So QL are power series which converge for modulus x less than 1. Once again, this modulus x less than 1, where does it come from? It comes from the fact that we have regular singular points at x equal to plus or minus 1. Okay, so don't lose sight of the original problem. All right, so we have the convergence, the region of convergence is this, and it follows the same recurrence relations as the Legendre polynomial itself. Okay, so we can obtain closed forms. This is, I think Laboni was asking this question. So can we call this as some function? This, is that right, Laboni? That was a question that you had asked, no? This QL, can we call it a function if it's a power series? That is a question. Is that right? Labani, can you hear me? Okay, so I think she's not able to hear me. So to answer that question again, I mean, I have already tried to answer that question some time ago, but I'll just show you some of these examples. This QL, how does this QL look like? There is a method called as a Wronskian method. I think you all are already familiar with the Wronskian method, maybe in one of your maths courses during your BSc. Okay, maybe the linear algebra course in BSc. I just want you to just go and have a look at your notes in your linear algebra from your BSc course. You will find that there is a method called as a Wronskian method. You can use this Wronskian method to obtain a functional form of this power series. So if I remember well, if I've understood the question that Lavanya had asked, she had asked was, can we write, just like how we have sine, cos and so on, sine function, cos function, these are functions and they have power series representations also. So can we call a power series as a function? So I think that was the question that she had asked. And the answer is, the more appropriate way to say that is, functions can have power series expansion. It's the other way around. Okay, not like, power series, are they functions or not? It's function, whether functions they have a power series expansion or not. So in case in case of sine and cos, we start with sine and cos and we go on to the power series expansion. But using the Wronskian method, it gives you the other way around. You starting from a power series expansion, you can go back to the functional form. Okay, you can obtain a functional form. So using this Wronskian method, we are able to obtain the functional form for some of these QL. So L equal to 0, we have Q naught, it takes this form. Now you see it's a logarithmic function, right? And we know that logarithmic function has got a power series expansion. So if you expand this as a power series, you will get Q0. If you expand this as a power series, you'll get Q1. If you expand this as a power series, you'll get Q2 and so on. Okay, so this is the closed form of QL, and I have plotted this Q0, Q1, Q2 and Q3. Let me show you the plots that I have over here. So these are some of the plots. Okay, let me reduce the size so that you can see it better. Okay, so these are the functional forms, the plots of the functional forms, and as you can see here, it converges. You see this x value, it lies between -1 and +1. It converges, this power series, it converges between -1 and +1. So this is Q0, this is how it looks like. Then Q1 is this orange part, This is how Q1 looks like. Then Q2 is the green curve. This is how Q2 looks like. And Q3, this red curve, this is how Q3 looks like. Okay, just for the sake of completion, I'm giving this plots also. Okay, so this, all of these plots we get it from the functional form using the Wronskian method. Any questions so far? Anyone? All right, so finally we come to the properties of Legendre polynomials, and we'll stop over here. So these are the properties. Okay, any special functions? We are interested in the Rodriguez formula, mutual orthogonality, recurrence relations, and generating functions. So these are the functions that we properties that we're interested in. First, the Rodriguez formula. If you remember, Legendre polynomials you can obtain by repeated differentiation. So you can differentiate this function x to the power x square minus 1 whole to the power L. Okay, so if I differentiate x square minus 1 whole to the power L, if I differentiate it L times, and whatever after differentiation whatever I get, if I divide it by 2 to the power L into L factorial, it will give me PL of x. Okay, so starting from this you can compute the Legendre differential equation of Legendre polynomial of any type. So you can just try it out. Let's say for the first few types you can just try it out on your own. So let me take the Rodriguez formula on a new page. So this is the Rodriguez formula, and let us say I want P0. Okay, I want P0. We know that P0. Okay, so to find P0. Okay, so how do you find out P0 of x? P0 of x, that means we are talking about L equals 0, right? So L equals 0 means, using the Rodriguez formula, P0 of x is equal to, we know that P0 must be equal to 1, okay, that we already know. So let's just verify if this is equal to 1. So P0 of x is equal to 1 divided by 2 to the power L is 0 times 0 factorial, then d 0th derivative divide d0 by dx0 of x square minus 1 to the power and 0. You can see everything becomes 1. This is 1, this is 1. 0 derivative means the function itself. Okay, so that 0 derivative means you're not doing anything. So this is raised to the power 1. So this entire thing, it will turn out to be 1. So P naught of x, we expected P naught of x to be equal to 1. Right, P naught of x to be 1, and we got 1. Let's try P1 of x. Okay, so to find P1, to find P1 of x, that is for L equals 1, then what do we have? So we have P1 of x, and that means this will be 1 by 2 to the power of 1 into 1 factorial into d to the power 1, that is d by dx only. So d by dx of x square minus 1, and L is 1. So we have to differentiate this. So what will that give us? So we have 1 by 2 to the power 1 is 2, 1 factorial is 1, and we are trying to differentiate this one. The differentiation of this is 2 into x. So this gives us x. So that is your Legendre polynomial P1. Okay, and just you try it out to find homework. Verify verify P2 of x using the Rodriguez formula. Okay, please try this out on your own. So that's the Rodriguez formula, which allows you to compute any of these Legendre polynomials very easily. You just have to differentiate. Be prepared for repeated differentiation. Then we have mutual orthogonality, that is the Legendre polynomials, they are mutually orthogonal over this range, and this orthogonality is expressed as this. So if you integrate PL and PM between minus 1 and plus 1, okay, where L and M, they could be different from each other, then this is equal to 2 Dirac, this is the Dirac delta function, delta LM. So what does this Dirac delta function do? Can anyone tell me? This is the Dirac delta function. Can anyone tell me? What does the Dirac delta function give us? It gives us two values. It is equal to 1 for L is equal to M. If both L and M, they are equal, it will be 1. otherwise it will be 0. Sorry. When L is not equal to M, it will be 0. So it means if L, only if L and M they are equal, then we'll have 2 by 2L plus 1. If L and M they are not equal, then this integral will straight away be equal to 0. Okay, is that clear? Do you expect this behavior? Do you expect this kind of a behavior? Yes, we do, right? Because PL and PM, okay, if let's say they are not, it has got, you can look at it from the point of view of the even and odd functions. Okay, when do functions become even and odd? And if you multiply those functions and integrate within this range -1 to +1, then if it's an odd function, then it will give you 0. If it's an even function, it will give you a non-zero value. So from there you can actually understand this mutual orthogonality. Okay. Then we have recurrence relations. Recurrence relations, basically, if you know the lower terms, you can find higher terms. You have 4-term recurrence relations. Okay, this is a 4 terms recurrence relation. That means it involves Pn prime, Pn minus 1 prime, and Pn plus 1 prime. It involves the derivatives. So this is a 4-term recurrence relation, and this is a 3-term recurrence relation. So we are not really interested in deriving this. Just I want you all to recollect that about these different recurrence relations. So we have 1, 2, 3, 4, 5. Out of this, the number 5, the E1, that is I find it very convenient because this one does not involve any derivatives. You can see here all the other terms. There is a derivative here. There is a derivative here. Here there is a derivative. Here also. Here we have a derivative. Here we have a derivative. But this last one, okay, the last one, there are no derivatives, so you can easily find out. In fact, this is the same thing which is also applicable for your this one also, the Legendre functions of the kind of the second kind. So from here, the same recurrence relation, it is applicable. So we can say n plus 1 q n plus 1. This is equal to, instead of p you put q, 2n plus 1 x qn minus n q n minus 1. Okay, just replace p with q, you will get the recurrence relations for the Legendre functions of the second kind. Okay, so that's about the Legendre functions. And finally we come to the generating functions. Now what is a generating function? It is actually a really cool idea. Okay, what it says is, there happens to be a function, there exists a function such that if I expand this function as a power series, okay, if I expand that particular function as a power series, then that power series, it will have coefficients as well as some term which is raised to some power. Those coefficients will be nothing but the Legendre polynomials. So you can see here, it has to be a function of 2 variables. One is obviously x, another one, let's say, is h. So the generating function, it's a function of x and h. So in case of Legendre polynomials, this is the generating function, 1 by root over 1 minus twice x h plus h square. So even if you forget everything about the Legendre polynomials, let's say you don't know the Legendre polynomials, at least if you remember this function, you will be able to generate this. Why? Because this function, you can obtain a power series expansion. So suppose I want to expand this in terms of h. Okay, so I want to expand this as a power series in terms of h. So how do I do that? This one, if I want to expand as a power series, so it will be simply summation, let's say some constant, okay, Cn, or rather I should say Cl h to the power L, right, where L goes from 0 to infinity. This is what it is. Now what is this Cl? Is this really a constant? Yes, it is a constant. Cl is a constant, but it is constant with respect to h alone. Okay, so because Cl is a constant with respect to h alone, this implies this Cl, it's a function of x. Okay, and it turns out if the function happens to be like this, then these different Cl, this constant, this Cl of x, they will turn out to be exactly equal to the Legendre polynomials. They will become exactly equal to the Legendre polynomials. So all you have to do is just expand it, and whatever you are multiplying with h to the power L, that will become the Legendre polynomial. So what I mean by that is this. So what I essentially mean by that is something like this. I write, let's say, this function. So 1 divided by root over, the function is 1 divided by root over 1 minus twice x h plus h square. What will this be equal to? If I open this up as a power series, we will get we'll get 1, okay, times h to the power 0, then we will get x times h, then we will get 1 x, we will get 1 by 2 times 3x square minus 1 into h square. The next term is going to be equal to 1 by 2 5x cube minus 3x into times h cube and so on and so on. Okay, this is how it will go. So if we expand this with respect to h, this is what we will get, and you can easily identify this is your p0, this is your p1, this is your p2, this is your p3. Okay, so it means this one can be simply written as p0 plus p1h plus p2h square plus p3h cube and so on. In other words, we can just write this as a summation of PL of x times h to the power L, where L goes from 0 to infinity. So it means all you need to do is just remember this. Even if you forget everything about the Legendre polynomials, no problem. At least if you remember this function, you can generate all the Legendre polynomials as coefficients of its power series. So that's why this is called as a generating function. Is this clear? Is okay. Now if this is clear, then you will find a use which I'm going to show you. That use is going to be really interesting, an application. Okay, this application again you will see next semester in your course on electrodynamics. So if I want to find out the inverse distance between 2 points in 3-dimensional space, okay, so here the generating function, it becomes very handy. So let us say I have a scenario like this. Okay, so I have this is the origin, we have the axis, y axis and the z axis. So this is one point. Okay, this point has got a position vector of r prime, and this point has got a position vector of r, and these two vectors r and r prime, the angle between them is theta. Okay, and so this is the separation between the two, right? So we have one point here, another point here, and the separation between these 2 points is r minus r prime. Do you agree? This is from your basic class 11 vectors, right? So if this is a one vector r prime, this is another vector r, then this vector, which is the separation vector, that is r minus r prime. Do you agree, everyone? Is this fine?
Yes, sir.
Okay. So if that be the case, okay, then I want to find out what is the separation vector. Okay, what is the distance between these 2 points? Okay, all I want to find out is the distance between these 2 points. How do you find distance? All I need to do is just find out the separation vector and take its modulus, because modulus of a vector is nothing but the distance, right? So all I need to do is just take the modulus of r minus r prime. So this is what I'm trying to find out, modulus of r minus r prime. So modulus of r minus r prime is basically this. How did we get that? Remember your class 11 again. So let's say I have a vector A and I have another vector B. So what is A minus B? A minus B is this vector, right? This is vector A minus vector B. So what is the modulus of A minus B? You need to know the angle between the two. So modulus of A minus B will be equal to under root A square plus B square minus twice AB into cos theta. If I want A plus B, modulus A plus B, then this is going to become a plus. Remember, class 11, you had done this when you had studied vectors for the first time in your life, right? So I have just used the same formula here. The vector A is r and the vector B is r prime. So we have A square plus B square minus twice AB cos theta under root. So that's why you get r square plus r prime square minus twice r prime into cos theta. Clear, everyone? So I have not done anything extraordinary over here. Okay, so now I want to find out the inverse of this separation. So that means 1 by modulus r minus r prime. That will be 1 by under root r square plus r prime square minus twice r prime cos theta. Okay, so if I take r common here, so what I have done here is, so we have 1 divided by, we have under root. Okay, if I take, let's say, r square inside the root, if I take r square common, then what do I get? If I take r square common, so this first one we are going to get a 1. The next term we are going to get r prime by r. So we're going to have r prime by r whole square. Then the next term will be 2. We have to take, we are taking r square common, so we have to divide by r square. So 1 r from the numerator will get cancelled out. So we are just going to have r prime by r into cos theta. This is what we will get. Okay. Now if I take this r outside, we are this r square, if I take it outside the root, we are going to get a r here. Okay, and what is left behind is this entire thing. So under root 1 minus 2 r prime by r into cos theta plus r prime by r whole square. Is this clear? This step, is this understood? So now let me define certain quantities. I'll call h is equal to r prime by r and x equal to cos theta. Okay, can I do that? Can I call x equal cos theta? Yes, I can, because if you remember, we are talking about Legendre functions. Legendre function, the range of values which we are interested in is -1 to +1. Yes or no? Those are the regular singular points, and the radius, the region of convergence for QL, that will be from -1 and +1. The region of convergence for the polynomial, for PL it is everywhere, but for QL it is between -1 and +1. Right. So if it's a linear combination, it is always going to be the smaller region of convergence. That is going to be the region of convergence of the solution of the differential equation. So here, because x lies between -1 and +1, and cos theta also lies between -1 and +1, so I can say cos theta, x equal to cos theta. So as a result, this 1 by modulus r minus r prime, it becomes, we have 1 by r times, and here in this quantity we have 1 as it is, 2 minus 2, and r prime by r, I'm calling it as h, and cos theta is x. So this is minus twice x h, and this is h square. Okay, and if you notice, this is nothing but the generating function, right? This is nothing but the generating function. Can you see that?
Yes, sir.
Here, right? The same generating function, 1 by under root 1 minus twice xh plus h square. So it's nothing but the generating function. Okay, so I can just replace, go ahead and replace this. The moment I see that this is a generating function, so 1 by r, it's a generating function, and we know that the generating function can be written as a power series expansion, where the coefficients are nothing but the Legendre polynomial. So the inverse distance can be written in this way. Okay, so if you remember this idea, the inverse distance is 1 by r summation, inside the summation, r prime by r to the power l, because that's what h is, into pl of cos theta. Okay, it involves the Legendre polynomials. Is this clear? So remember, inverse distance can be written in this way. Is this clear, everyone?
Yes, sir.
Okay, so now you might be wondering, why are we trying to find out the inverse distance, right? Because what could be the practical application of this? Yes, there is a physical application. The physical application is, if I want to find out the potential due to a charge. Okay, so let us say the same scenario. It is exact same scenario. What I did was, I put a charge here. Okay, I put a charged particle here, and I want to find out what is the potential at this point. Okay, so that's just what I did. So we put a charged particle at r prime, and I want to find out what is the potential at this point. Okay, so how do you find potential? What is the formula for potential? Oops. What is the formula for potential? Potential is K Q by R, right? This is the formula for potential. So what is this potential going to be? This potential is going to be equal to 1 by, K is 1 by 4 pi epsilon, right? Q divided by, what is R? R is the distance between the charge and this point. And what is this distance? R minus R prime, right? Yes or no? So this is the potential that we are looking for. Correct, everybody?
Yes, sir.
Okay, so here we have Q divided by 4 pi epsilon naught times 1 by R minus R prime. Okay, so this is what we have. Now recognize this, we have already evaluated this, right? 1 by r modulus r minus r prime we have already evaluated. This is nothing but the 1 by r times the summation of r prime by r to the power l into Legendre polynomials. We already know the answer. So you just have to plug in that one, and that will give you the potential that we are looking for. Okay, so this is the potential due to a point charge. So 1 by q by 4 pi epsilon naught, and 1 by r minus r prime, I just replaced it with the expansion that we have arrived at, and this gives us, we have this r I combine with this one, and this summation, it is simply L is equal to 0, this is going to be 1, so we have P0 plus r prime by r into P1 plus r prime by r whole square into P2, and so on. This is what we have. And then a special cases, if the charged particle is at the origin, okay, if the charged particle is at the origin, then r prime will be 0, right? The charged particle, where was the charged particle? The charged particle was here. Now if I take the charged particle and if I place it at the origin, what will happen to r prime? R prime is going to become 0, correct? So let's apply this, r prime equal to 0. So if put r prime equal to 0, so this will become 0, this will become 0, this will become 0. Everything will become 0 except what? Except this first term. First term will be P0. And what is P0 equal to? P0 is equal to 1. So it's going to give us this familiar node formation. Remember KQ by R, which I told you about? We are going to get that KQ by R expression. Is that clear, everyone?
Yes, sir.
Any questions?
No, sir.
Okay, so this brings me to the end of this lecture. So in the next class, which I'm going to take